You know from chemistry everything about atoms. Every atom basically looks like that. This is a hydrogen atom, the simplest atom. It has only one proton in the middle and one electron orbiting that proton. And we can write all equations we need, and we know from UI 105 and 106 to describe the situation. Newton's law, that's Newton's law. Mass times acceleration, which is centrifugal acceleration, equals force, which is Coulomb's force. We can calculate the energy because it equals kinetic energy plus potential energy. And that potential energy, why is minus here? Because you multiply a negative charge and a positive charge. Positive number times a negative number gives you a negative result. If you combine these equations, you actually can calculate the total energy. It turns out it's a negative number. Why is it a negative number? Because hydrogen atom is stable. So if you want to take away the electron, we have to do some positive work. And that's why the energy is negative. We can calculate momentum. We can calculate angular momentum. The problem is that electrons, protons, all tiny particles have a very special properties, wave properties. And this model doesn't tell us yet anything about wave properties. If we could look inside of the atom, we would see something like this. We couldn't find a specific electron. It's a kind of cloud. We cannot ever say where is the electron now. That's impossible. The location of the electron can be described only in terms of probability. There is a certain probability to find the electron here or there. However, lucky us, what we can calculate, we can calculate the wavelength related, de Broglie equation gives the wavelength related to any specific momentum. And we can make an assumption. Niels Bohr made that assumption first to explain visible spectrum. Very natural assumption. If an electron is a wave, a specific orbit exists only if we can fit a standing wave in that circle. That's it. So, not any orbit is possible. Only that orbit which fits a certain standing wave. We know standing wave, yeah. Standing wave on a spring, now it's standing wave on a circular spring. That's it. So we basically know all the properties. Turns out, if we combine this expression with all expressions from simple mechanics, we can calculate those specific radii. Not every radius is possible. Only a specific set of radii is possible. Plus, we can calculate what? We can calculate all specific values for momentum, or energy, or angular momentum, or kinetic energy, or potential energy. All those physical variables do exist. However, now they cannot have any possible values. They can have only certain values. We say energy now is quantized. Radius is quantized. Momentum is quantized. Everything is quantized now. And, well, if we know the energy, possible energies of the electrons, we can ask the question, what's happening when the energy changes? Well, first of all, how could it be changed? We can shine a light at it. We know when a photon encounters an electron, the collision is happening, Compton effect, photoelectric effect. Well, in general case, electron doesn't have to get away. It would just jump in energy. We say an electron jumps from a lower energy level to a higher energy level. And of course, the law of conservation of energy tells us how the energy of a single photon is supposed to be related to the change in the energy of the electron. Energy doesn't disappear. So, if electron absorbs some energy, photon loses some energy. That's what we call absorption. If electron loses some energy, in that case, the photon is created in that process, and that photon must have only a specific values for energies. We actually can say that for any photon emitted by a hydrogen atom, energy of the photon is supposed to be proportional to 1 over n1 squared minus 1 over n2 squared. These numbers just come from this equation, which come from this equation, and we know, well, it's basically a condition for a standing wave fitting in this circumference. This number is some integer, 1, 2, 3, 4, 5, doesn't have any end. So the energy levels could be calculated. Well, this is the same value for the hydrogen. We just have to use different numbers. It's about negative 13 electron volts, 13.6. Doesn't matter. However, every next level has a higher energy. Why is it higher? Because the actual value becomes greater than the previous one. We use negative numbers, like in this picture. We start from negative 13.6 related to n equals 1. We call it the ground state energy, the lowest energy. Then we plug in n equals 2, and that gives the level number 2, negative 3.4. Of course, negative 3.4 is a larger number than negative 13.6. So it's kind of tricky thing in terms of negatives. Then n equals 3 gives another level, and another, and another, and another, and another. Eventually, when n equals infinity, we get to 0. So if we know the ground state, ground. Nothing wrong today. Okay. If we know this energy, we can ask the question, how much work is supposed to we do to take away the electron? We call it ionization. Well, the final value of the energy of the atom in this case is 0. The initial value equals this. Work, which is done, is supposed to be final minus initial. That gives this. So basically, you take this value and you're multiplying by -1. That gives you the amount of work you're supposed to do to ionize the atom. Well, we also can ask a question. Okay, for example, let's say the atom is in a ground state. If we apply a photon with the energy of 9 electron volts, can this photon excite this electron? Well, the lowest level is at negative 13.6. To excite an electron, we're supposed to supply the energy equal 13.6 minus 3.4, which is 10.2. That's the smallest amount of energy we should supply, because there are no energy levels between the first and the second. These energy values are restricted by the law of nature. So if the photon doesn't have 10.2 energy, nothing happens. Photon is traveling through. However, if it has 10.2 or more, in that case, electron could absorb that energy and it could jump to the second level or to the third. So if you have a photon with energy about like 15 electron volts, what would happen? Well, electron could jump to the second level, and a photon with lower energy would still be traveling away, so it would change its frequency. Now I think 15 is enough to actually jump to the third level, but still not all photon energy will be lost. A photon is lost completely when the photon energy equals exactly the difference between two energy levels. Exactly. In that case, electron takes all energy and photon might disappear. Now, let's say electron is in excited state. What can happen? Well, eventually, it's supposed to go down to the ground state. How many options does it have? Well, it could jump straight to the ground state. Could it? Yes, why not? What would happen? In that case, we would observe a photon emitted with energy equals 13.6 minus 8.5. That will be the energy of the photon. It must be equal to the energy difference for electron. But that's only one option. What else could happen? Well, it could jump to this energy level first and eject a photon. However, again, after this, it could jump down and emit another photon. Why not? What else could happen? It could jump like that first and then down. Two more photons. Or it could jump from this level first to this level and then down. Two more photons. So if your electron is jumping down from the level number 4, this is how many different photons could be emitted in that process. And of course, we always can calculate if we need exactly the wavelength and the frequency of all possible photons emitted by the electron. And for each specific frequency, we could observe the specific spectrum line. Now the spectrum is linear. It's not a white light spectrum. Yeah. White light spectrum looks, well, it's spread all over the colors. Now we just see a red line or a green line, etc., etc. And what's important is each element has a very specific set of lines. There are no two elements with the same set of lines. It's like a fingerprint for a person. So if you look at the spectrum, you can say what kind of element is presented over there. You look at the sun and you see helium. That's how helium was actually found first. People were looking at the sun and they found that there are some lines which couldn't be explained by any known element. And they say, okay, that's supposed to be some kind of a new element. Let's call it helium. Helios. Sun. Well, and if we go deeper inside the atom, what we see? Nucleus. The nucleus is made of protons and neutrons. That's not a new fact for you, you know that. So if you're adding up together the number of protons and the number of neutrons, the result we call the mass atomic number. Different isotopes have exactly the same number of protons, but they might have different number of neutrons. So for example, there is a helium-2, 4, and there's a helium-2, 5. What's the difference? Both, well, helium, both have the same number of protons, 2. But this one has only 2 neutrons, and this one has how many neutrons? 3. 5 minus 2, 3 neutrons. And well, this element actually wouldn't be stable, it would be decayed eventually. So, as we know from many, many experiments, all elements could be divided in 2 parts. Well, heavy elements normally don't have any stable isotopes. Light elements have stable isotopes. If we have unstable element, what is happening? It decays. It splits in parts, basically. And the rate of the decay, the number of disintegrations per second, the number of decays per second, that's what we call activity. We use usually international system of units, so 1/second, number of decays per second, we call it pictorial BQ. If you had a radioactive material and you would be measuring activity, there are devices which do that. I'll bring them on Wednesday. On Wednesday we're going to have 3 demonstrations. So today just pure theory. But if you could use that device and over 2 seconds you would measure 128 decays, what would be your activity? This is the definition. So 128/2, 64 BQ. That's what it is. However, if you wait longer than 2 seconds, an hour, 2 hours, 3 hours, and you would measure the activity again, your number would be different. It's always getting smaller. Why? Well, because the number of active elements left always over time getting smaller and smaller. So let's say we start from 100. Do you work? You know. Now you do. You start from 100 of radioactive elements. The black dot shows a decayed one. So it is not the original element anymore. Let's say red dots represent the uranium-238. So when it decays, it's not uranium anymore, it's thorium. And if you wait long enough, here on the graph you can see the amount of elements left undecayed. at this time. Here you can see how many left undecayed and how many had decayed. And of course, for any element, if we wait long enough, eventually these numbers become equal to each other. When does it happen? It happens exactly at the moment when a half of the initial elements had decayed. Close enough. So now we started from 1,000 radioactive elements. And right now we have left exactly a half of them. This time exists for all elements. You just have to wait, maybe sometimes long enough, maybe years, maybe thousands of years, but it happens. So every radioactive element has that particular time when exactly a half of elements have decayed. This time has a name, we call it a half-life, and this, well, function, which looks like that, could be described mathematically in a very simple terms. This is one mathematical way to write it down. When we write an expression like that, we use a number E. E, which is the base of a natural logarithm. When we use E, this number in the top, in the front, we call decay constant. However, we could write the same law differently. I'm just going to show it. And we could write the same law in terms of the base 2. And now, instead of using decay constant, we would be using the half-life. Basically, what it says is, you start from initial number. If you wait one half-life, you get left a half of that number. If you wait one more half-life, you get left a half of a half. And if you wait another, you get a half of a half of a half, etc., etc. So this is the radioactive law in terms of how many halves do you wait. This number n is 1 or 2 or 3 or etc., etc. The morning is good. The day is sad. No more physics class later. Well, let's start from a question. This is the law for radioactive decay, and this Greek letter lambda is called the decay constant. And here we have 3 graphs. The black curve represents radioactive decay for some element with a specific decay constant. The question is, which of 2 extra graphs, the red one or the blue one, represents the radioactive decay with a larger decay constant? Okay? Is it clear what the question is about? We need to compare 2 decay constants. Number one represented by the black curve, and another one which is supposed to be larger than the first one. Okay, so the decay constant shows how fast the decay is happening. So in this situation, of course, the red one represents the decay which is happening faster. The rate, the rate of the decay, we call it the activity, well, absolute value of it. The rate of the decay actually is equal to the slope. So if you compare two slopes, this one, you can see here that activity is larger, decay happening faster. Well, for now, eventually, if you look at the end of the process, here in that region, actually, this slope is going to be more horizontal. So at some point, well, the change happens, and you have a slope-related equation in your homework problem. Remember this. Now, this equation, which involves the decay constant, is the least convenient equation to use when we deal with radioactive decay. Much more convenient equation looks like this. We know that, by definition, half-life is time we have to wait to get only half of the initial amount of radioactive elements left. So the same graph, exactly the same graph, we could read differently. Here, after one half-time, we have left a half of the initial amount. Here, after one more half-life, we have left a half of the previous amount, which is a quarter of the initial, etc., etc. So this number n gives us how many half-lives should we wait. That's it. And this number n, of course, is related to the actual time interval and the half-life of a particular element. So if we have counted the number of half-lives, we can multiply by the half-life to get the time period. Or vice versa, if we know the time, we can divide it by the number of half-lives, and that will give the value for a half-life. Well, of course, for all important elements, we have half-life measured. It ranges from fractions of a second to billions and billions of years. And this is just an example, which let's do together. It's very convenient sometimes to spend a minute and to write all powers of 2. Because if you're using half-life, you're using powers of 2. So here in this example, you already have it given to you. But if you don't have it, you can always spend a minute and write it. It's simple, yeah? You just multiply it by 2. Etc., etc. So multiplying by 2 is an easy task. So the next power will be 2048, etc., etc. Well, so what's happening here? Now, well, now means t equals 0. That's the initial time. So, and you have this particular amount of radioactive elements. 1 hour later, which means that's actual time, 1 hour you wait. You have left 32 radioactive atoms. So, well, we could ask, for example, how many radioactive elements had decayed? 10, 24 minus 32. That's how many disappeared. Okay. Now, the law says 32 is supposed to be equal to 10, 24 times 2 to this. This is how many half-lives should we wait to get from 1024 to 32. Well, and of course, we can solve it mathematically. 1024 over 32 equals this, which in turn equals this. 1024 equals 2 to the 10th, 32 to the 5th. How do we deal with fractors like that? We subtract powers. That's supposed to be equal to 2 to the 5th. So n equals 5. And of course, if you have a table like that, you could count down. 1, 2, 3, 4, 5. It takes 5 applied to get from 1024 to 32. Well, now, if you know that it's been 5 applied and it took 1 hour, what is the value for a half-life? Well, these are your possible answers. 7 minutes, 10 minutes, 12 minutes, 15 minutes, and 17 minutes. That's my second question. So I'm going to erase this. So make your mind, pick a number. Or maybe not, maybe I'll correct you. So 7, 10, 12, 15, 17. No. You are seems faster than me. So on. Okay, let's try again. 7, 10, 12, 15, 17. Did I get it? Finally, a perfect answer? 100%? No. You make this day even sadder than it is already. So, 1 hour equals 5 half-lives. 60 minutes over 5 minutes. You can't combine hours and minutes. You have to use the same units. Gives you 12 minutes. That's a half-life. So every 12 minutes, the amount of the radioactive element getting cut in half. Well, okay. Next question. So, from initial time, how much time would we have to wait until the last radioactive element decays? Well, there are different ways to do that. You can count half-lives. So you start from this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In 10 half-lives, you have left 1 atom, but you still have 1 radioactive element. So you have to wait 1 more until that last element decays. And now you have nothing left. If you would try to set it up mathematically, first of all, common mistake is writing 0 equals this times this. If you want to apply the law of radioactive decay, you cannot set it to 0. The smallest number you can set it is 1. So that doesn't work. You can calculate how much time you would have to wait until one atom is left undecayed. And that will give you, again, 10. And now, if you are looking for time that last atom decays as well, you have to add one more half-life. So 11 half-lives. Now, how many atoms decay between this and this? Well, in this case, again, we can think about it differently. Well, first of all, probably the easiest way is just to calculate N24 and N124. N24 is how many atoms left after, well, we've been waiting for 2 half-lives past here, and 1 hour 24. 1 hour 24 is 5 plus 2 more, 7 half-lives. That's supposed to be this times N2. Well, N1 is 2, and 2 is 7. Now, how many atoms had been decayed? Well, that's the difference between these two. So, 1, 2. If you wait for 2 half-lives, this is supposed to be 256. If you wait for 7, so 1, 2, 3, 4, 5, 6, 7, that's supposed to be 1, 2, 3, 4, 5, 6, 7, that's supposed to be 8. So, in 2 half-lives, you have 256 atoms left. In 7 half-lives, you have 8 atoms left. So how many decays between this and this? 256 minus 8. Yes. 1, 2, 3, 4, 5, 6. Because 1 hour equals 5 half-lives. 24 minutes equals 2 more half-lives, because each is 12 minutes. So 5 plus 2, that gives me 7. Basically what I did, I have calculated N2 equals, well, you have to use consistent units. So 1 hour 24 minutes is actually 84 minutes. And you have to divide it by 12 minutes, because this is the value of half-life, so half-life. Any questions? Well, this is an example of a very important practical application of the law of radioactive decay, carbon dating. What we know is that any breathing, living tissue has a certain amount of radioactive carbon-14. The stable isotope of carbon is carbon-12. It has 6 neutrons, 6 protons. So if you have some extra neutrons, it's radioactive. But its half-life is about 6,000 years. So we can use this fact to figure out how old some kind of a sample is now. Here, a sample of wood. So we have a very old piece of wood, and its activity is 0.22 becquerel. So what we do? We take exactly the same sample of wood from a living tree. So we assume that some years ago, this wood would be active exactly like current wood is active now. So the living breathing piece of wood give us the value for initial activity of this piece of wood, which is old now, and the activity of which is lower. So this is the activity initial, this is the activity current. The law of radioactive decay relates numbers of elements. How we can rewrite it in terms of activity? Well, activity is just the actual value of radioactive elements times the decay constant. So we can multiply the whole equation by lambda, and that gives us this exactly same relationship for activity. So all we need to do now is just count how many half-lives had passed. So how many? Let me ask this question to the class. Okay? I realize. So 1, 2, 3, 4, or 5. How many half-lives had passed between the activity 0.88 becquerel and the activity 0.22? Okay, numbers don't change anymore. 2. That's correct. All we have to do is again apply the law of radioactive decay in terms of activities. So 0.22 over 0.88 is supposed to be equal to 2 to some power. Well, it's easier to invert the whole thing. So 4 is supposed to be equal to 2 to the number of half-lives. That's supposed to be 2. And now, if we know that a half-life is about 6,000 years, 6 times 2, about 12,000 years old, this piece of wood. Well, any questions? Because now we go to the next topic. So that, is a picture of a nucleus, how we think it would look like if you could see protons and neutrons, protons positively charged, neutrons not heavily charged. And if you would be using international system of units, the masses for all elements would be really, really kind of small. So we don't usually use international system of units in a problem like that. We use an atomic mass unit. By definition, an atomic mass unit is equal to 1/12 of the mass of the carbon-12. So, of course, there's a conversion factor, but again, it's much easier sometimes to convert atomic mass units into energy than into kilograms, because mc squared equals E. So one atomic mass unit equals 1.5 megamillion electron volt. Now, using atomic mass units, calculations usually are easier. This is just a list of possible conversion factors. So one atomic mass unit times c squared gives 1.5 megajoule. Now, we know many different forces by now. None of these forces actually is strong enough to hold neutrons and protons together. The problem is that protons actually so close to each other, so the force of electrostatic repulsion is very, very strong. to hold them up together, to overcome the force of electrostatic repulsion, we should use some new force, very strong nuclear force, which has a name, strong nuclear force. That's the name of this strong nuclear force. And in order to hold them together or take them apart, we have to do some work. And if you want to calculate that amount of work, or we can calculate the amount of energy which binds, holds nucleons together, what we have to do, we have to find the mass deficit, or mass defect. What is it? The idea is simple. Let's say you have helium. It has 2 protons and 2 neutrons. So if you actually weigh a nucleus of helium, you can measure a specific number. How do we do it? We could use a mass spectrometer. We can accelerate it. It's a positively charged particle. Place magnetic field, measure radius, that's it. So that's one way to measure the mass of this nucleus. However, we could actually measure the mass of each proton and each neutron and add them up together. Turns out, numbers don't match. Turns out, well, in this example, it's not about helium, it's about carbon. There is a difference. Very small difference, but a difference. In atomic mass units, the nucleus of carbon-12 should weigh exactly 12 atomic mass units. But if we calculate just the mass of 6 protons, etc., 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 we get a slightly different number. Why? Well, the law of conservation of energy says that this is supposed to be equal to the amount of energy we have to, well, spend to take apart that nucleus, or the amount of energy which holds, which binds particles together. So this energy has a name, binding energy. And to calculate the binding energy, that's all we have to do. We have to compare 2 masses. The mass of the actual mass of the nucleus and the total mass of individual particles. There is always the difference. And this part always has more mass. So if you subtract one number from another number and you multiply by speed of the light squared, that gives you the number of the binding energy. Normally, in physics, you would use a binding energy per nucleus. So this graph represents a binding energy per nucleon for all elements. An example is related to this particular isotope of uranium. So how do we calculate the binding energy? Well, if we know that it has 238 nucleons, we just take the number from binding energy per nucleon, multiply by the number of nucleons, that gives the binding energy. What is it again? It's the difference between the rest energy of this nucleus and the total rest energy of all 238 individual nucleons. Well, this is my next question. When we make changes, well, different kind of changes could be made. The easiest one, the decay. You take a radioactive element, you put it on a table, you wait it decays. What kind of change is happening? Well, you start from one element, and you have at least 2 different elements. That's one possible change. That's what we call a spontaneous reaction. We don't have to do anything, we just wait. Another kind of reaction is, well, kind of backwards. What can we do? We can take two elements, collide them together, and see what's happening. In that situation, so we have to start from at least two elements. It could be two different nuclei. It could be a proton and a neutron, anything. We wait and we see what might happen. Well, so in this situation, we might end up temporarily, usually, with some kind of a combined element and eventually it decays again. But that's a different kind of reaction, not spontaneous one. This is transduced reaction. So, if we talk about spontaneous reaction, wait, don't do nothing, it decays. Which do you think would be the correct relationship between the masses before the reaction? And well, here we might have some elements and we can add up together the rest masses for each dotted particle. So that's what we call after the reaction or right mass. So which of these two conditions, which one of these two conditions is true for a spontaneous reaction? Okay, so not so obvious question. So as I said, let's think backwards. Let's say you have two elements and you collide them together to get one. This fact is action. It means that we actually doing some work. We need to accelerate. So we actually are adding some energy. So in terms of the masses, this rest mass should be larger than these rest masses together. If we wait and they decay is happening and we count rest masses together, in that case, M right is supposed to be less than M left. Plus, normally, what is happening, they actually move fast away from each other. Why? Well, by the law of conservation of energy, M left c squared is supposed to be equal to M right c squared plus, well, that kinetic energy. So if we could find elements for which this mass difference is actually large, that means we could get a lot of kinetic energy from each reaction like that. And that's what is happening in atomic plants. When uranium, well, 235, for example, decays, those particles travel very fast. What means fast? Fast means they're hot. So we could use those particles to heat up, for example, water, boil it up, and that steam we could aim at a turbine, and that's how it works in general. Now, okay, so these are just possible examples for different reactions. What's important is, for any reaction, we always, in addition to law of conservation of energy, can apply the law of conservation of charge. And I got one slide. So, if you add together number of protons before reaction and after reaction, you must get the same number because charge cannot disappear. So in any reaction, like 0 plus 5 equals 3 plus 2, or, well, this gamma represents a highly energetic photon. A photon doesn't have any charge, so the charge is 0. 0 plus 12 equals 11 plus 1. So law of conservation of charge always relates these numbers. So if you have a reaction, and let's say you don't know a specific element, let's say this is a question mark. So what can you do? You can set up an equation, x, well, usually it's z, and this x. So 1 plus 6 supposed to be equals 7 plus z. That will give you the value for z. Well, in this equation, in this particular example, that's 0. That means this particle doesn't have any charge. What particle doesn't have any charge? Well, it could be a photon or a neutron. We don't talk about neutrino, so in our problem, it's either a photon or a neutron. Now, to figure out what particle actually is the result in this reaction, we can compare these numbers. Mass number is related to energy. Energy stays the same. Kinetic energy never is large enough to change this number. So what we have to say is 1 plus 13 is supposed to be equal to 14 plus x. Well, in this situation, x equals 0. Well, it means this particle doesn't have any mass number. And there is only one particle like that. It's a photon. If you had, well, one, 0, that would give you a neutron. 1, 1 gives you a proton. 2, 4 gives you helium or alpha particle. We'll talk about alpha, gamma, beta very soon. So law of conservation of energy and law of conservation of charge tells you, well, at least what possible reactions could happen. This is an example of a very important reaction, nuclear fusion. What we do, we collide two particles together. It's important because we believe this is what is happening inside the stars. That's how they get the energy. Well, they both positively charged, so they repel. However, if they're really hot, energetic, fast moving, they actually can get so close to each other, so the force of strong nuclear force getting stronger than electrostatic repulsion. So they form temporarily a new element which shortly decays, and these particles now so energetic. So well, if we could use this reaction here on Earth to solve all our energy problems, all of them. However, so far, no one can make this reaction stable. It could be easily made unstable. That's a hydrogen bomb, but that's too dangerous. Another important reaction, nuclear fusion, looks like this. Again, it's an induced reaction. But now we use a neutron which makes the uranium-235 nucleus decay faster than it would decay originally. So what's happening? After the decay, we get more neutrons than before. So 1 neutron, 3 neutrons. And each of these neutrons now can encounter another nucleus of uranium-235. And each of these could induce a next decay. These particles are really fast moving. So this reaction, if we don't manage it, happens really quickly. And that is how atomic bomb works. And I have an example, a mechanical model of this situation. Here, what I have is just a testing set of mouse traps with a ping pong ball on top. So it represents an atom of uranium-235, and this represents a neutron. If I drop 1 neutron into this system, it starts a reaction in 1 atom. And that atom releases a new neutron, and that neutron releases new neutron, and again, and it happens. Well, it's a mechanical model. Almost instantaneously. So if I hadn't had this shield, I would be killed. Most probably. So we don't want that. We want to manage the speed of this reaction. How can we manage the speed of the reaction? Very simple. We have to take away extra neutrons, and that's how atomic plant works. In atomic plant, we use beryllium rods, which take away extra neutrons, and the reaction now is happening much slower. So sometimes something goes wrong, unfortunately. But basically, by now, we know everything about how to manage nuclear reactions. So any atomic plant, at least contemporary plant, should perfectly work, and not very dangerous if managed correctly. And of course, sometimes, well, if natural disasters happens, well, now we know we have to be ready for very strong quakes, very large tsunami. Well, there are 3 specific decays which are, well, practically and historically very important. Alpha, beta, M. Well, historically, a piece of uranium was used, and photoplate covered in black paper turned out to be damaged. So it couldn't be light because the black paper prevents it from light. So, and well, it started a lot of new discoveries. What we know is that some of these particles have positive charge, some of these particles have negative charge, some don't have any charge. And for each particle, alpha, beta, gamma, we know it's either a helium nucleus or an electron or a positron, which particle with exactly the same mass but positively charged, or a photon, very energetic photon. Well, this is a magnetic field. A magnetic field tells us the charge of a particle. That's it. We just have to apply the right head rule. And when the beta decay is happening, something like that, that means the result of the decay gives us either an electron or a positron. You can read negative beta decay, you can read positive beta decay. It means that in the end, no matter what had happened here and here, there is a beta particle, either plus or minus. So this particle is much lighter, almost 2,000 times lighter than a proton. So we don't assign any mass number to this particle, but we could assign +1 or -1 depending on what particle it is. For electron, -1, for positron, +1. Well, and etc., etc., etc. Very standard notations. For any reaction, as I said, we always can apply the law of conservation of energy and the law of conservation of charge. So in this situation, we in one equation describing all possible decays, alpha, beta, gamma. I'm not going to answer this question. It's simple. We know that before and after the reactions, these numbers are supposed to be equal to each other. So E is supposed to be equals question mark plus X. That's it. So question marks is Z minus X. And depending on what we get, well, it could be gamma, alpha, or something else. Here, I have an example of a beta decay and a gamma decay. This device we call a Geiger counter. It counts decays per second. So we actually can hear. Sound tells us that now through this area there is a particle which traveling hits it. Well, this is what we call a background radiation. Unfortunately or fortunately, we're surrounded by radioactive elements. One, we are not, they're everywhere. The question is about concentration, how many radioactive elements are around. Plus, we always have cosmic rays penetrating the atmosphere. Some of those ray particles, cosmic particles, so energetic they can get through the Earth. You know, imagine that you are right now sitting here and some particles are traveling through you. For everyone, that's inevitable and unavoidable. This is a good thing, and this is a bad thing, because now we know some of those reactions might lead to some mutations, and those might be a positive thing, or might be a negative thing. Well, if we take something radioactive, we can hear that the intensity of activity is much higher. Well, of course, we cannot count by listening to this, so there's a scale here which gives a number. And imagine that people used to eat from plates like that. It's a regular plate. I have a set. I used to have. It's painted in pink, and a lot of paint used to have some uranium in it.